Greetings and welcome to Physical Science at Hack. In this video, we will work through the sample problems for Chapter 10 on chemical reactions. So we'll see a few different calculations here and a few other that do not involve calculations, as we've had in previous questions. So let's start out here with this first one, which says to identify the following as empirical or molecular formulae. And if there's anything that's uncertain, we want to put a question mark by it. So how do we tell if it is empirical or molecular? Well, if you recall, one way to look at these is that if it is the simplest whole number ratio of atoms that you can possibly have, then it could be empirical, but it is certainly not molecular. Molecular ones are ones that are going to have ones that are definitely molecular, in other words, should be ones that do not have whole number ratios. So let's find a couple here that are molecular, and that would be something like B, which has C2H2. Well, that is not the simplest whole number ratio that you can possibly do. You could simply write CH. So this would be an example of a molecular. And you could just explain that as it does not have the simplest whole number ratio. C18H18 would be another one that would definitely be molecular. Because it is not the simplest whole number ratio, you can divide each of these by 2 and get another value, get values that are non-fractional. Now, other ones we might have to look at a little bit more closely. We can also look at whether they are ionic or covalent bonds. Recall we did that with the electronegativity previously. So let's look at these. We're often going to get an ionic bond when we have elements from one side of the periodic table with the other side. So magnesium and chlorine is going to be an ionic bond. And if you have an ionic bond, then you are going to have an empirical formula. So this one would be empirical. Same thing with barium and fluorine. Those are on opposite ends of the periodic table. You can check the electronegativities, but that is going to be ionic and therefore empirical. Now the last ones we have, what kind of bond are we going to have here? This is going to be a covalent. So it will be a molecular bond. So it's a covalent bond will give us molecular formula. Now the last one I've saved in there is CH4. That is the simplest whole number ratio. If we look up the electronegativities for carbon and hydrogen, we find that this would be covalent. But this would be our question mark. We don't know whether that is the actual molecular formula. Is that actually a methane, or is it simply an empirical formula that represents a much more complicated compound? So we don't know that in this case. So that's going to be our one that we would mark with a question mark here. So let's move on to our second question. Our second question says, what is the mass percentage composition of elements in each of the following compounds? Now, this is going to require a calculation in each case. So let's start off with the first one here. A is fool's gold, which has iron and sulfur. Now, the first step to do is to find out what the atomic mass is of each of these. And of iron, the atomic mass is 55.9 units. The atomic mass of sulfur is 32 units. The first thing we have to do is to find the total, the molecular weight of these. So we got to put them together, and we're going to add 55.9 plus 32, but there's 2 sulfurs in each, so this is going to be times 2. So the total weight is going to be 55.9 units plus 32 times 2 is 64 units, which equals 119.9. So that is the total molecular weight of this compound. Now we want to find the percentage of each of those elements. So we're going to take now, let's start with iron. Iron is 55.9, so we just take the 55.9 units and divide it by 119.9 units, and that gives us that will give us 46.6% iron. So 46.6% of this is iron. Now you can do the same thing for sulfur. You could take 32 times 2 and get 64 units. You could divide that by the 119.9 units, and you would find out that that is 53.4% sulfur. So 53.4% sulfur. Now the other way you could have done that was just to know that the two have to add up to 100. So whatever you get here plus whatever you get here, this value, one of your answers, and this value, the second one, they have to add up to 100. So if there's only two elements in it, once you figure out the first one, you could also just as easily say that 100 minus, or 100% minus 46.6% equals 53.4%. So you can either do the calculation as we did over here. You have to do it once, but if it's only two items, then you can skip the second time and just know that the two have to add up to 100. If you do the actual calculations, you might find in some cases that they apparently don't add up to 100, and that's just due to rounding errors. So let's look at the second one here, boric acid. We have hydrogen, we have boron, and we have oxygen. Hydrogen has a mass of 1 atomic unit. Boron has a mass of 10.8 atomic units. Oxygen has a mass of 16 units. So again, we want the total. What is the total mass of that molecule? And we're going to need 3 hydrogens, so 3 times 1 unit, plus 1 boron, so just plus the 10.8 units, plus 3 oxygens, so 3 times 16.0 units. And that would give us 3 plus 10.8 plus 48 units, which gives us a total molecular weight of 61.8 units. And now we do the same thing that we did previously. Now we are going to take, for hydrogen, what is the percentage of hydrogen? Well, there are 3 hydrogens, so 3 times 1, there's 3 of these, 1 of these, and 3 of these. So for hydrogen, we would simply take 3 units divided by 61.8 units, which would give us, and then multiply it by 100, and that would give us 4.85% hydrogen. For boron, we would do 10.8 units divided by 61.8 units. Divide those, multiply by 100, and that would then give us 17.5% boron. Finally, for oxygen, we do 3 times 16 because there's 3 atoms, so 3 times 16 is 48 units. Divide that by the 61.8 total, which gives us the percentage for oxygen of 77.7% oxygen. So we can add, if we add those up, you should get something very close to 100%. If you ever do these calculations and the 3 do not add up to 100%, it's a good idea to go back and check because you've probably made some calculation error along the way. So at the end, all of these should add up to 100%. Now we have 2 more to look at here. Let's look at baking soda next. So baking soda has sodium, hydrogen, carbon, and oxygen. Sodium is 23 units. Hydrogen, we've already said, is 1 unit. Carbon is 12 units. And oxygen is 16 units. So now we want the total. Well, we need how many of each? So how many do we have of each? We have 1 sodium, we have 1 hydrogen, we have 1 carbon, and we have 3 oxygen. So we have to add those up accordingly. And that would give us 23 units for sodium, plus 1 unit for hydrogen, plus 12 units for carbon, plus 3 times 16 units for oxygen. So if we add that up, that's 23, 24, 36 units plus 48. So 36 units plus 48 units gives us a total of 84 units for the molecular weight of these. Now we have to figure out the percentage of each, and we do that exactly as we did in the previous steps. We will take, for sodium, we will do 23 units divided by 84 units, which gives us 20. When we divide those and multiply by 100, we will get 27.4% sodium. If we do the next one, we would do hydrogen, would be 1.0 unit divided by 84 units, which gives us 1.2% hydrogen. Carbon is going to be 12 units divided by 84 units. And again, I'm not writing in the multiply by 100. You always multiply these by 100. And that would give you 14.3% of carbon. And finally, oxygen is going to be 16, but 16 times 3 is 48 units divided by 84 units. And that would give us oxygen of 57.1%. Now we have one more of these we want to look at. Let's mark all of our answers there. So we have 4 values this time, and again, if you add all of those up, you should get something really close to 100%. It won't be precise because of rounding errors. The last one we want to look at is aspirin, which has carbon, hydrogen, and oxygen. Now we've already done all of these elements before, so we know that carbon is 12 units. We know that hydrogen is 1 unit. And we know that oxygen is 16 units. So let's add them up. What are the quantities that we have? Well, we have, in this case, we have 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. So we've got to add all of those up together. And that would give us 9 times the 12 units for carbon plus 8 times 1 unit for hydrogen plus 4 times the 16 units for oxygen. And if you add all of those up together, you're going to get 180 units. Now we have to figure out the mass percentage of each. So let's do carbon next. Carbon would be, we would take 9 times 12. So 12 is the weight, and where there's 9 of those, so 9 times 12, and divide that by the total weight of 180 units. 9 times 12 is 108, and 108 divided by 180 multiplied by 100 will give you 60% of carbon. Next, we want to look at the hydrogen. Hydrogen, we do it exactly the same. There's 8 of those times 1 unit divided by the 180 units, which is the same for everything. Once you calculate that, it remains the same. 8 divided by 180 and then multiplied by 100 will give you 4.4% hydrogen. Lastly, we got to do the oxygen. Oxygen, there are 4 of those atoms. Each of them is 16 units. And we divide that by 180 units. And that will give us for oxygen 35.6% oxygen. So the final answers there in the boxes would be the percentages for each of these. And again, if you add them all up, a good check to make sure you didn't make any silly mistakes is to make sure they do add up to 100. So let's move on to our third question here. Our third question asks us to write some balanced chemical equations. So now we have to balance these chemical equations. And let's look at how we can go about doing that. Well, first of all, let's look at the first equation. To balance it, we can change the coefficients in front of each of these, and we have to get the same number of atoms on each side. So in this case, if we look at this side, we see that there is 1 sulfur atom and 4 oxygen atoms. This one has 1 sulfur atom and 3 oxygen atoms. There's nothing I can do to this oxygen to get that to balance, because I can't change this. Ideally, you'd want to just change this to a 1 and then everything would be perfectly balanced, but that's not the chemical reaction. So the next thing we can try doing is doubling these. We've got to make the sulfurs the same, but we could try putting a 2 in front of each of these. Then the sulfur is still the same. So we now have 2 sulfurs on this side. We have 2 sulfurs on this side. On this side, we now have 4 oxygen atoms, plus 2 makes 6. And on this side, we have 6. So our balanced equation would read 2SO2 plus O2 yields 2SO3. And that equation is now balanced. Now let's look at the second one. In this case, we have to again try to keep everything balanced. So we have to look at, first of all, the phosphorus. We have phosphorus, 2 of them on this side and only 1 on this side. So we'd need to start with a 2 there. Let's try that. Okay, so 2 phosphorus would then give you 2 phosphorus on this side, 2 on this side, and you have 2 oxygen on this side and 5 on this side. So we need to get some more oxygen here. Putting a 2 in front of oxygen would make it only 4. So we have to actually go a little bit higher. What you'd want to put there is a 2.5. Again, all of the coefficients have to be integers. So we want to go then with, we could try putting, for example, another larger number there. We may have to up the number of oxygens. What we want to do is get an even number of oxygens on this side so that we can fix this and make it correct. So ideally, to do that, let's make this an even number. So let's put a 2 here. That gives us 4 phosphorus and 10 oxygen on this side. But we still only have 2 phosphorus here. So now we have to cross off that 2 and replace that by a 4 so that we have 4 phosphorus on both sides. So 4 phosphorus and 4 phosphorus. We have 2 oxygen and 10 oxygen. Now we can do that. Now we can actually replace this with a 5 and give us a balanced equation. And our balanced equation would then read 4 phosphorus plus 5 oxygen yields 2P2O5. And if you count up the number of atoms on each side, we are again balanced. Our third example here to look at is aluminum and hydrochloric acid. So Al plus HCl gives us AlCl3 plus H2. So we have to look again to balance everything. Let's look at what we have. We have 3 chlorines here, and we want to get 3 chlorines here. So as a start, we could put a 3 on this side. Now that gives us aluminum has 1 on each. Chlorine is good, but we have 3 hydrogens and 2 hydrogens. So again, we're going to have to double things. We're going to have to try to get this to be an even. We have to get these to be an even number. So instead of 3, we could actually double this. Let's get rid of the 3, cross that off, and make it a 6 instead. We could have 6 chlorines because we can easily make this 6 chlorines. We have 2 aluminums. Well, we can make that 2 aluminum. Now that gives us hydrogen, 6 hydrogens on this side. And now that it is an even multiple, we can easily say that there's 3 hydrogens on this side. And that gives us a balanced equation, which simply says 2Al plus 6HCl yields 2AlCl3 plus 3H2. All right, number 4, as we continue on these, we have NaOH and H2SO4 combining together. So let's look at what we need to do to combine these. Well, we start out again. Look at some of the elements that are not in many places. We don't want to look at oxygen right away because it's all over the place. Let's try to get the sodiums and the sulfurs balanced. Well, sulfur is good, so let's not touch that right now. Sodium has 2 on this side, so let's put a 2 over here, and let's see what that does. 2 sodiums, that's good. 1 sulfur, that's good. Now we have to look at the oxygen and the hydrogen. What are we off in terms of oxygen and hydrogen? On this side, we have 5 oxygen and 3 hydrogens, 1, 2, and 3. On this side, we have 5 oxygens and 2 hydrogens. I'm sorry, counted that wrong. Let's start over again. On this side, let's mark it over here. Oxygen, we have 5 oxygens. That's not correct. That's actually 6 oxygens. On this side, we have hydrogen. We have 2 here, and 2 here gives us 4. And sometimes writing these down can help you keep track of things. On this side, we have now 5 oxygens, so we need 1 more. So we have oxygens on this side are 5. Hydrogens are 2. So essentially, in order to balance this, we need 2 more hydrogens and 1 more oxygen. Well, that's exactly what water is. So if we put a 2 here, that will make our equation balanced, because now we will have the same number of hydrogens and oxygens on both sides. And that will give us our balanced equation of 2NaOH plus H2SO4 yields Na2SO4 plus 2H2O. All right, on to number 4 here. Let's look at the next one. So let's look at our next one here, which says Fe2O3 plus CO gives you Fe plus CO2. So we want to try to balance this. Well, we have 2 irons on one side and 1 on the other. So let's start off by putting a 2 there. That's always a good start. On this side, we have 1 carbon and 1 carbon. So the only thing we're left looking at is oxygen. On this side, we have 2 oxygen atoms. On this side, we have 4. So we have to try to get more oxygen atoms on this side. Well, how can we do that? Well, initially, you can think you put a 2 there. That gives you 4 oxygen atoms and 4 oxygen atoms. But now you've messed up carbon. Now we have extra carbon here. So that is not quite going to work. So that 2 is not going to be correct. We have to do something where we can change both of them, because I have no way to add just back 1 carbon atom. Let's try a 3 oxygen atoms. We could try 3 here. So 3 carbon dioxides would give us 6 oxygen atoms on this side. On this side, we have 4, so we'd need 2 more. That would put a 3 here. And then the carbons actually balance, because you have 3 carbons and 3 carbons. So everything will actually balance, and we would get our balanced equation of Fe2O3 Let's write that again. Fe2O3 plus 3CO yields 2Fe plus 3CO2. Now our last one to look at here for this section says we're taking these compounds and combining them together. So let's look at our different compounds we have to look at here. First of all, we have magnesium on both sides. We have 3 magnesiums here, only 1 here. So let's put a 3 there in front of magnesium. PO4, we can actually look at that individually. Instead of looking just at phosphorus and just at oxygen, we can consider PO4 as 1. We have 1 PO4 on this side and we have 2 on this side. So a good bet is to put a 2 in front of that, giving us 2 PO4s there. And let's see what that does for everything else. That magnesium is still good and the PO4s are still good. So this is all great. What we need to just make sure is how many waters we need. Well, on this side we have 6 hydrogens plus 2 more here, so we have 8 hydrogens on this side. And we have how many oxygens? We have 4, 5, 6. Sorry, not counting the PO4. We don't count the PO4. So on this side we actually only have what, 6 oxygens. So let's see. Let me check that again. Sorry, let's go back. Okay, so let's look at the oxygen and the hydrogen. What do we have on each side? Again, we want to ignore the PO4 here because we've already balanced that. We don't want to count that. We just want to look at the hydrogens and the oxygens. So in this case, hydrogens, we have 6 here. And we have how many here? We have 2 in each of these, and we got 3 of those, so that's 6. So there's 12 hydrogen atoms on this side. Oxygen atoms, we ignore this part. We have 2 times 3 is 6. So we have 12 hydrogens and 6 oxygens. That would just be 6 water molecules. So we can make this a 6, and we now have a balanced equation. So M3Mg OH with the subscript 2 plus 2H3PO4 yields Mg3PO4 with the PO4 having a subscript of 2 plus 6H2O. So let's look at a couple more of these balancing equations. These ones, now you have just the part of the equation to balance. So we have to come up with the products. In this case, when we burn a hydrocarbon, we end up with the combustion reaction, and we will get carbon dioxide and water. Now we can balance this equation if we look at what we need to add here. We need 5 carbons, so we need 5 carbons on this side. We now have oxygens. We have 12 oxygens here and only 2 here, so we need a 6. And if we just need to balance our oxygens. Carbon and hydrogen are good. We have 10 oxygens on this side, 6 on this side. That's 16, meaning that we need 8 oxygen atoms, giving us our balanced equation of C5H12 plus 8O2 yielding 5CO2 plus 6H2O. Now looking at our next one, if we combine hydrochloric acid and sodium hydroxide here, we will get sodium chloride and water. So if we combine an acid and a base, we get a salt, in this case sodium chloride plus water. Now what do we need to do to balance? Well, we have 1 chlorine, 1 chlorine. We have 1 sodium and 1 sodium. That's great. We have 2 hydrogens and 1 oxygen. And guess what? That equation is balanced as is. There is nothing else we need to do. So what it comes out to be is simply HCl plus NaOH yields NaCl plus H2O. Now our next one, if we're going to combine aluminum and the iron oxide here, we are going to get Al2O3 plus iron. Now we want to balance these. We have 2 irons on this side. We need 2 on that side. We have 2 aluminums on this side. We need 2 on that side. There's 3 oxygens and 3 oxygens, and we are balanced. And that would give us our balanced equation of 2Al plus Fe2O3, giving us Al2O3 plus 2Fe. Our fourth one to look at here, we have iron and copper that are combining and giving us Fe. These are going to give us FeSO4, FeSO4 plus copper. So we have a replacement reaction there where the iron is replacing the copper. And what do we get? Well, if we want to balance these, let's look at it. We have 1 iron, 1 iron, we have 1 copper, and we have 1 SO4. Everything is perfectly balanced and we are done. So our balanced equation is just Fe plus CuSO4 yielding FeSO4 plus Cu, and it is done and balanced. This one shows would give us actually no reaction. So this one would actually give you no reaction because both compounds are soluble, so there's nothing to balance there. So the last one we want to look at here, C6H10O5 plus O2, is going to yield us, again, we're going to get carbon dioxide, a combustion reaction, plus water. And all we have to do is balance it. So let's look at what we have here. We have 6 carbons, so we're going to need 6 carbons on this side. We have 10 hydrogens, so we're going to need 10 hydrogens on this side. We have, then we just got to make sure the oxygen's balanced. So on this side we have 5 oxygen and 12 oxygen, or 17 oxygen. There's 5 of them. That leaves 12 more here. And that means we need a 6 coefficient here. And our balanced equation would simply read C6H10O5 plus 6O2 yields 6CO2 plus 5H2O. Now we have one more section here to look at these. So let's look at the last few reactions that we have to look at here. In this case, these are replacement reactions. So we are going to take the sodium and the water, and we are going to combine them, and we are going to get sodium hydroxide, NaOH, plus hydrogen gas. So when we combine these, we have 1 sodium and 1 sodium. We have 1 oxygen and 1 oxygen. We have 2 hydrogens and 3 hydrogens. So we really want to write this. What we'd love to do is to write this as 1/2. Unfortunately, that is not permissible. So what we have to do is, if we can imagine writing that as 1/2, we really could leave it as, make it a 1 and just double everything else. So in reality, we could leave this as a 1 and put a 2 here and a 2 here and a 2 here, and you will find out that that balances. You have 2 sodiums, you have 2 oxygens, you have 4 hydrogens, and you have 1, 2, 3, 4 hydrogens. So your balanced equation would be 2Na plus 2H2O yields 2NaOH plus H2. Now the next one is actually another that will give you no reaction. Gold will not interact with the hydrochloric acid, so there is no reaction here. Hydrogen is much more stronger binding with this than the gold, so it will not actually give any kind of reaction. So in that case we have no reaction and therefore nothing to balance. Now the other ones we will get something to react. So with the aluminum and the iron here, iron and chlorine combination will give you AlCl3 plus Fe. And if we want to balance that, do we need to do anything? Well, we have one aluminum, we have one iron, and we have 3 chlorine. There is absolutely nothing to do, and your balanced equation is just as it was written. Al plus FeCl3 yields AlCl3 plus Fe, and you are balanced. Our last one here, zinc and copper chloride. If we put those together, we are going to get ZnCl2 plus Cu. And again, one zinc, one copper, 2 chlorine, and boom, we are done. And your final answer is simply going to be zinc plus CuCl2 yielding ZnCl2 plus Cu. So I hope this has given you some examples working through the sample questions and the balancing of equations for this lesson. And until next time, have a great day, everyone, and I will see you in class.